So determine which of the following equations are polynomials. So based on those definitions from last video. So our first one, we've got a base that's x to the power of something with a degree 5. Yep, that's a whole number. We've got a constant. Yeah, that's a polynomial. Here though, our base is actually 5 and the exponent is the variable. We can't have that. We cannot have our exponent as the variable, so nope. Technically, yes, this is just a constant, but it is a polynomial, so yes. Here, I'm looking at this right here. This is what catches my eye right away. We have an exponent 1/2. No, cannot have exponents that are fractional, so no. Here we have a fraction 1/3, but it's a coefficient. Coefficients are allowed to be fractions. All the degrees are whole numbers. This is a 1 here, so yes, that is a fraction. Absolute value of x. Well, that would have a sharp corner. That would look something like this. So no, we can't have that. It has to be smooth and continuous, so no. Here we have square root of x. Now it feels wrong right away, and if we write this out as a power, so it's 1/2, well then definitely not, no. We can't have fractional exponents, so no. Now can we have fractional coefficients? Is square root of 7 a real number? Well yeah, it is. So therefore, yes, this is a polynomial. Now our final one, this is a fraction, and we have a variable in the denominator. That's one of the restrictions. We can't have that, so no. So now that we've looked at what is a polynomial, let's look at how those graphs look. So we have functions with odd powers and functions with even powers. And then if we look at this chart, we have if it's a positive or negative. And that's going to be our leading coefficient, is positive or negative. So first degree, so that's just a linear graph. We can see that as it's going right, it's going up, and to the left, it's going down. Now if it's negative, those are both flipped. Now for a second degree, so that's a parabola, if we have a positive a value, our parabola is going up, and both ends are going up as well. However, if that leading coefficient is negative, then we have that parabola going down, and both ends actually go towards negative infinity. So let's go to our cubic functions then. So in our cubic, we have, it's a degree 3. If it's a leading coefficient that's positive, then our right-hand side of our graph is going to positive infinity, our left-hand side is going to negative infinity. The opposite is true if it's a negative leading coefficient. So then our left side is going to positive infinity, and our right side is going to negative infinity. Finally, let's go to fourth degree. So here, this can look a lot like a parabola. Sometimes that's just evened out. This one has a little bump in it. When we're looking at this, it's the same properties though. Leading coefficient that's positive, both the left and the right side both go to positive infinity. And if it's a leading coefficient that's negative, they both go to negative infinity. Okay, our final one, fifth degree. This one acts a lot like a cubic. So we can see actually all the odd powers all kind of behave the same way. So if we have a leading coefficient that's positive, then the right side goes up to positive infinity, the left side of the graph goes to negative infinity. And the opposite is true if it's a leading coefficient that's negative. So then answering this question, what is the most amount of x-intercepts for each of these? Well, if it's a first degree, we only have 1. If it's a second degree, possibly there's 2. There could be less. There could be only 1. There could be 0. But the max amount is 2. Then our third degree, well, the most actually is 3. We're always going to end up at least with 1 in that case, but the max will be 3. Fourth degree, the most we can have based on this picture is 4. And then finally, fifth degree, hopefully you see the pattern at this point, it's going to be 5. That's going to be our maximum. Now before we move on, we should do a little bit more comparison of like quadratic versus quadratic or quartic versus quartic. So quadratic, our regular quadratic is just a nice smooth parabola. That's our parent function y equals x squared. And then our quartic is y equals x to the power 4. You can see it looks very similar to our parabola. It's a little bit flatter here at the bottom. But then how do we get those bumps that we were looking at before? So if we go back here, how come this one showed like a bump? And then yet, if it's just a degree 4, it doesn't have that bump. Well, it's all going to be about how these terms are. These terms kind of determine where that bump is, how high it goes, but it'll still maintain that overall parabola-like shape. Now if we compare cubic versus the parent function of the cubic versus something that has an extra term, you're going to get that bump with that extra term. So same thing, but it's still going to behave overall like a cubic function. The same for a quintic, so that's the degree 5. You're going to see it behaves like an odd power function, but as soon as you add some other terms in there, so all these extra terms, that's where we're getting all of these bumps from, is from these terms. But overall, as this graph gets closer to infinity, this leading term starts to take over. That to the power of 5 is so much more the power of 4. Then as we get closer to the x is bigger and bigger and bigger, and it's getting closer and closer to infinity, it's taking over, and so therefore we have that same general shape as just the parent function, closer to the end, or closer, sorry, there is no end, closer to infinity as the x gets increasingly large. Alright, we've been using the words zero root and x-intercept maybe a little more liberally than we should be, so here's some exact definitions. So a zero describes a property of a function. So the key thing there is a function, so when what x value makes this function equal to 0. Whereas roots is what makes an equation equal to 0. So what x value makes the equation equal to 0. And then the x-intercept is the property of the graph. So these locations here on the graph where the height is 0. So then when we're speaking about zeros, we're going to verify that this equation p of x is equal to x squared minus 4x minus 5, that these are actually zeros. So this is a function, so we're going to substitute -1. So p of -1 is equal to -1, so we got brackets there, squared, minus 4 times -1 minus 5. So -1 squared is 1. We get plus 4 minus 5. Well, yep, that's equal to 0. So therefore, -1 is a 0. Okay, checking the second one then. So we're going to look at when p of 3, what the value of that is. So we get 3 squared minus 4 times 3 minus 5. So 3 squared is 9, minus 12, minus 5, and you get -8. So that's definitely not a 0 then. So therefore, 3 is not a 0. Now what if we're not given the zeros? Well, this is what we did a lot in 20-1. So I want to find these zeros of this function. Well, that we're going to factor first. Now this is PSA1 because the leading coefficient is 1. So our product we're looking for is -5. Our sum is -4. So our answers are going to be -5 and +1. So therefore p of x is going to equal x minus 5 and x plus 1. Okay, so therefore our zeros are x equals 5 and x equals -1. So now that we remember what a 0 is or a root is, there's actually this property called multiplicity. So when we solve the equation, it's possible that we have two of the roots or zeros actually being the same. And that tells us something about the graph. So when we had parabolas and they were perfect squares, so when I say perfect square, maybe you ended up with like f of x is equal to x minus 2 squared. Well, here we have 1 0 and it's 2. But it actually has a multiplicity of 2 because really this is x minus 2 times x minus 2. So our 0 here is 2 and it's also here as well. So if we look at that, a root with multiplicity of 2 will touch the x-axis but not cross it. So then I know that this equation right here might look something like this, where my x-axis is going to come across right here. So we can actually sketch a little bit nicer of a graph using this idea. Now if it has a multiplicity of 1, it just passes straight through. And then if it has a multiplicity of 3, it's going to act a little bit like a cubic function as it crosses that x-axis. So you see it does this little curve on it. Alright, well let's take a look at some functions that have already been factored for us, and let's determine the zeros and state the multiplicity of them. So here our zeros are x is equal to -3 and 1. Both of these have a multiplicity of I'm just going to put mult, and this is only 1 for each of them. Okay, let's look at our second example. So here, x is equal to 3 then, and this one will have a multiplicity of 2. Here, x is equal to 1, that's our 0, but it's going to have a multiplicity of 3 because we're going to have actually 3 of these x minus 1s. And then finally, our last function, so x can be equal to -1, or it can be equal to 2. Now we have a multiplicity of 2 for this -1, because that would occur twice, and then this 2 would only occur once though.